Hi everybody. So I'm trying something new today. I have the Google Meeting open at the same time as I have this stream going up. So if you want to have a discussion, then feel free to get in there and join me in the meeting. We'll see. Maybe this is excessive, but let's give it a shot and try it out. And so I have many things open right now. So if you want to send a message to me in the chat, if you want to send a, if you want to send stuff to me anywhere, that's all fine. I will find it and I will talk to you about it. Uh, whatever. Okay, and so yeah, so let's get started today. I would like to start by talking about the precipitation unit. So this is the solubility unit. I was discussing with a student yesterday that that this is a unit that is actually kind of an easier version of what we were doing before. So we were just finished the equilibrium. So now we're going to start talking about specific types of equilibrium. And we're going to do two different types of equilibrium. The first one is going to be the precipitation equilibrium. We've kind of done general reaction equilibrium already. And then we will discuss the neutralization, acid-base reactions, and the equilibrium of those afterwards. So this has a little bit of preamble here about how water is essential to life on Earth. More than 2/3 of the Earth surface is water. Our bodies are water, right? So 65% to 90% of our cells are made of water. And so that means that many of the reactions that we are interested in happen in water. Those reactions that happen in water are known as aqueous, a terminology we've already used. Remember that aqueous reactions have properties of concentration. So these have, this implies a concentration. So that implied concentration is really important because that is going to be essential to the ideas of equilibrium. So if you recall, water is a polar molecule because the hydrogen atoms and the oxygen atoms do not share the electrons evenly. The oxygen is more electronegative than the hydrogen, resulting in electrons in the hydrogen and oxygen bonds lying more towards the oxygen than they do towards the hydrogen. And we looked at this again when we discussed the electron density and electronegativity. So oxygen, I believe, is in like the 3.5s for electronegativity, and hydrogen is like 0.5. Okay, so with the aqueous solution, so when we're talking about water, we've talked about in the past that oxygen is more electronegative, right? High electronegativity. It's pretty much the second highest electronegativity. The second highest electronegative element on the periodic table, and then hydrogen is pretty low. It's not the lowest electronegative element ever, but it is on the lower end. And so the result here is a very strongly polar covalent bond. So this is called a dipole, and we draw a dipole arrow from the positive end. So here the slightly positive hydrogen up towards the negative, which would in this case would be the oxygen. And we usually draw those along bonds. So this is a dipole moment. And if you have multiple dipole moments, like in water, then you can actually use sort of a vector addition, just like we would in sort of physics class, and we can take these two and we can add them together to show that there is a general dipole moment in this direction. And so this general dipole moment in this direction is going to mean that the electron density is very highly located at the oxygen end, and the hydrogens are essentially oxygen poor. This allows other oxygen molecules to come around and attract themselves to those hydrogens. And in fact, this is where the concept of hydrogen bonding forms, is that every water has a little dipole moment, and so every water is pointing towards somebody else's hydrogen, and then that dipole moment is pointing to the next one, pointing to the next one, and this gives water its extra strong interconnection. When we dissolve an ionic compound in water, the substance dissociates into the aqueous positive and negative ions. The positive ions are attracted to the negative side of the water, and the negative ions are attracted to the positive side, and the ions become surrounded by water molecules or hydrated. The substance no longer exists as a compound, but as freely moving ions. And so one question is, why would this possibly happen now that we have some concepts of, things only happen if there's energy to be gained or lost? And in this case, we get to replace hydrogen bonding. So if we had let's put you're going to use this example here. So in this example, on this side of the universe, before this reaction, kind of in quotations, before the sodium chloride breaks apart, we have some ionic bonds inside the sodium chloride, and we have some hydrogen bonding, and some dipole interactions. So dipole, these are going to be what we call intermolecular forces. So they're between molecules. Intermolecular. So that's the dipole interaction is actually considered one of the weaker intermolecular forces. Now, if you want to drop a note in any of the chats, I've got them all open in front of me. So feel free to get in there and drop a comment in any chats. I've got Classroom, I've got meetings open, I've got the live stream chat open. So feel free to drop a question in there. Now, when we form the sodium and chlorine as aqueous molecules, we change our forces. So we lose, you no longer have ionic bonds. So I'm going to try to represent that. Ionic bonds. These ionic bonds have been lost. So those are gone. But we have gained a new type of bonding, which is called an ion-dipole interaction. And the ion-dipole interaction is generally considered to be stronger, in fact, a very strong intermolecular force. And at the same time, you actually haven't lost any, relatively speaking, there's so much water present that we haven't even really lost we have not lost the hydrogen bonding or the dipole-dipole interactions. So dipole, and hydrogen bonds. Still present. So we've got, so the dipole-dipole interactions, the hydrogen bonds, those are all still there. And now we've gained an ion-dipole interaction, which is a very strong intermolecular force. Is it energetically as strong as an ionic bond? Well, that's going to depend. There is a side thing here that we didn't really talk about. So these would all be relative to delta H. So these are all sort of energy, right? So these are energy. So we're talking about delta H here for the most part. There is a side piece of this, which is disorder, and a concept I really wish we introduced in this course, and that is also known as entropy. And when you separate molecules from their organized state into the aqueous state, you are increasing the entropy. And generally, this increase in entropy is what is really going to drive the dissolving action. So the universe likes disorder, and so the aqueous systems are naturally disordered. So that's the real reason that things like salt will naturally dissolve. It's going to be some sort of interaction between these two concepts. So you've got the concept of the energy stored in the bonds. Are you gaining or losing some of that energy stored in those bonds? So in the case of sodium chloride, for example, you might have some fairly weak ionic bonds, but some fairly strong ion dipole interactions. So there's a general drive to the right because moving that way gives you better bonding, right? More stable bonding. So more energetically favored ion dipole interactions. And then you also have the benefit of it becoming disordered. And so that disorder is also going to drive that reaction forward. Some cases, like say lead phosphate, for example, lead phosphate has an incredibly stable ionic bond, and it actually requires a lot of energy to break that down, and not the amount of energy that you'll gain from that disorder. So something like a lead phosphate is going to stay solid, stay stuck together, and very little of the lead phosphate is going to be high enough energy to actually break away from its ionic bond. It's just too strong, and there's not enough of a benefit for that ion dipole interaction on the other side. So write the dissociation equations for the following reactions. So we are talking about dissociation equations here. That's really the whole goal. We don't have to get it too far into this entropy enthalpy discussion. That is, as I mentioned at the top there, where it's not a concept we actually cover in our class. So potassium chloride, notice that this lesson is also trying to test you on whether you remember how to write your ionic formulas. So, or write a formula based on the ionic name. So KCl will break apart into K plus, which is going to be aqueous, plus chlorine minus, which is going to be aqueous. And in fact, almost all of these single charged ions, they break apart very easily. Magnesium chloride, and oh boy, I think we could actually make some conclusions about why that might be if you really think back to the beginning of our course. So magnesium chloride is going to break apart into a magnesium 2 plus. So notice that we have to include the two positive charges because magnesium has two chlorine ions attached to it. So that means that there's going to be two of those chlorines minus, and these are aqueous. So this is all we're looking at. Now, it might have been a while, but this is a chemical that has a polyatomic ion. So that sulfate is polyatomic. So we have to think that it stays together. The idea being that in the SO4, you have a bunch of covalent bonds. And covalent bonds are typically so strong that there is no gain to breaking them and trying to form some other type of bonding, not without an extreme amount of energy put in. So we get 2 sodiums out of that. Each sodium is a first column element. So that means that it has only a single charge. The sulfate, you might have to look up, but if it has 2 sodiums for that sulfate, then there must be a charge of 2 minus. And I gotta remember that we are talking about the phase symbols this time being really important, so we do have to write them. They should be written on the line, a little bit of a space between the symbol and the chemical formula, and they should be written at full scale. Full scale, lowercase. So solid. Ooh, look, I forgot another one. Okay, please, if you do find that there are a couple of old worksheets out there where people broke the rules and they put subscripted phases. I'm not entirely sure what happened there. I think it might be something in some textbook somewhere that incorrectly wrote the formulas that way, and it's spread all around the world. I find worksheets from all over that have the formula subscripted, but the official guidelines stated in the IUPAC is that the formula should be the phase symbols should be full size. So occasionally I see a little like something like this, and that seems to be only found in high school textbooks, and I'm not sure why. It's actually in our official document for one of the grade 9 or 10 courses, and it makes me mad every time I see it. So that's Al3 plus, aqueous plus, and then OH minus. This is the only one that's a little bit funky how we write it. Usually we try to put the charge as close as we can to the element it comes from, but because of the way we write OH, we write it always OH for hydroxide. I don't know, it almost makes more sense to put HO, but that's just how it is, and I don't have a good explanation. There's a couple more. Lead chloride. That. If you have any questions, feel free to ask. I'm just filling out formulas at this point. Okay. And if you're watching this later, then feel free to pause the video at any time and do these equations by yourself. Now, I guess we should talk about this. So if you are in a case where you don't know how to write these formulas, then remember that you can write out the lead and the chlorine, or iron and chlorine. And then when you have a letter code like this, or a numerical code like this, this is telling you that is a 3+ ion. Chlorine is 1 away from a full shell, so that means it only needs 1 extra electron to be full shelled. So that would make it a single charge. And then you can try, sometimes this works, to do a crisscross to find your formula. So I bring the 1 chlorine down, which means that I have 1 iron, so I don't have to write a number. And I bring the 3 down to write out the 3 for the chlorine, like so. Clean up so you don't show your hand that that's how you did it, and then move on to the next part. And then simply for this part, we're just writing the atom out. Don't forget that 3+ charge, and writing out the 3 chlorines on the right. Every time you write out a chemical formula, if your compounds on the left were neutral, then the charges on the right must add up to be neutral too. So we have no charge, and here we have 3+, and we have 3 times -1, so that also gives us 0 charge. So always do that double check, make sure your reactions are balanced. Okay, so a precipitate is a case where the amount of energy gained or lost from changing from the solid form to the aqueous form is not really sufficient. And so the reaction ends up not being favorable to turn into an aqueous solution. So precipitate reactions are one type of aqueous reaction that is important to both nature and industry. The formation of structures in limestone caves and some gemstones are the result of precipitation reactions. The scales that form in hot water pipes or kettles are also the results of precipitation reactions. Water purification plants often use precipitation formation followed by filtration as a means of removing impurities from drinking water. One of the ways we did chemical testing in our analytical lab was we would actually take an aqueous reaction and we would choose some sort of reactant that we knew reacted with the ions in our solution, and we would add that reactant until we saw precipitate form. And so it was a form of titration, really. You could titrate to the formation of a solid. So these ionic solids are not very soluble in water because the attraction between the ions is greater than the attraction between the water and individual ions. So the amount of change in terms of the formation of disorder and the attraction of and the formation of those uh, ion dipole interactions is less. So usually we're kind of thinking about the ionic bonds or ionic bond strength here, is uh, greater than the ion dipole, the potential dipole interaction. That's probably generally the driving force, and uh, and I'm going to put in that entropy part. Entropy changes. So for example, when a solution of aqueous silver nitrate and aqueous sodium chloride are mixed, the two clear, colorless solutions form a cloudy mixture. The cloudy mixture clears as a white solid settles to the bottom of the container, and that white solid will be silver chloride. There's a lot of other really cool ones. There's a really nice toxic one that we can watch a video on, and I'll post a video of it, and that is the formation of lead chloride. And I'll see if I can find it. So let's just see, lead chloride formation. It's a cool experiment where you can do you can do it as a rain. I thought it was lead. This is the one. So this is what it looks like. And so you can actually do this reaction. This reaction is so fast and that you can actually take two jars, hold them up in the air, and then pour them. And as they collide before even hitting the container, you'll see the formation of this yellow precipitate up here, and that'll hit the water as a precipitate and fall into the solution. And so this is two clear solutions forming lead chloride. So this is lead chloride, and you would have lead nitrate plus usually sodium chloride is fine. And these are clear, and these would both be aqueous. I didn't leave myself enough space to write that. And then they would form a solid precipitate. Typically, solid precipitates are not clear. They will be colored of some sort because they have a different density than the liquid. Sometimes they're colored in nice bright colors. Sometimes they're colored in just white powder. So when we mix the two solutions, the force of attraction between the silver and the chloride ions is stronger than the force keeping them in solution. I agree with that. so the is stronger than the force keeping them in solution. And when the two ions come into contact, they form this compound silver chloride. Eventually, the number of ions joining together becomes so large that the water cannot suspend them, and they settle to the bottom as a solid. The process is in which ions leave solution to form an ionic solid is called precipitation. So when ions leave a solution to form an ionic solid, it is precipitation. We can go back to Unit 1 and make some assumptions about this. So we have sodium and chlorine, right? Sodium is a relatively large element, or a large ion. Chlorine is a relatively small one. And so the distance between these is, some value of R. But silver is much closer to chlorine on the periodic table. It is down a row, but it is a little bit closer. So silver should be just a hair smaller than chlorine, or than sodium. And so when we put them side by side, they're going to be just a hair shorter, and that just a hair. So we'll call this one R. Let's call this RAgCl, and we can call this RNaCl. And we would expect that R of NaCl is probably just a little bit bigger than R of AgCl. And so this little shrink in R means that from the Coulomb attraction, so Coulomb attraction is higher for AgCl. And I'm gonna stand by that until someone sends me an email later. It says, "Hey, by the way, I looked up the values," which I'm now tempted to look up right now. Silver ionic radius. What do we got? 172. Okay, here's gonna go. 172. And sodium ionic radius. Yes. Oh, doesn't that feel good when it pays off? I made a bold call, and it worked out. I can't believe that. Whoa. I was really worried that was going to be recorded, that I made this call out. But yes, so that totally adds up. It all fits together now. That the silver is much smaller, and then the sodium almost like 10, 15% smaller, almost 20% smaller, I guess. And so that is enough to mean that the Coulomb attraction is higher. There's also another effect when we're talking about this sodium being a little bit wider, right? So 227. You can fit more waters around the sodium molecule without them having to crowd in on each other. And so you get more ion dipole interactions. So more ion dipole interactions. If you replace that with a little tiny silver, same charge, right? But now you can only fit, say, in my little doodle here, let's just say we can only fit 4. Should have made my waters bigger. So, and then this one be less ion dipole interactions. So it affects both sides of that equation. You have the side where the silver is dissolved. If the silver's other partner is something that doesn't want to hang out with it, like silver and nitrate, they don't really like each other anyways, then that's of course fine. When it's in water, the benefit's there. But when you put it into a solution with the chlorine, the silver and the chlorine will find each other, and they will that high attraction will not be able to break apart again from the formation of these weaker ion attractions. So notice from the diagram that the sodium and nitrate ions remain in solution. Since the ions separate in solution, they are allowed to react separately. The sodium ions and nitrate ions do not participate in the reaction. They just stand around to watch a show. Ions that do not participate in the reaction are known as spectator ions. So these are ions that don't have better bonding than the ion-dipole reaction of being aqueous. So there forms a bunch of rules. These are rules that are essentially developed from the ideas of certain elements have really strong ion-dipole interactions, and certain elements don't. So, or especially with water. So for water at 25 degrees, we can assume that all of the group 1 elements are going to always prefer the ion-dipole interaction. They're always going to prefer being in solution. There is one example of potassium perchlorate, which is an exception by being somewhat. This is one of the problems with these rules. Is they're rules with a strong. There should be a strong pair of quotations on them. And we're going to learn a much better approach than depending on these rules soon enough. Most compounds of chlorides, bromides, and iodides are also water soluble because chlorine, bromine, and iodine all have strong dipole interactions. So they have strong ion dipole interactions. They love water. The exceptions are if you present them with something that's a very small, strongly charged ion. So those would be copper, lead, silver, and mercury. Lead and mercury have very strong charges, right? They have 2+ charges. And silver and copper are relatively small metals. So those two typically, these ones don't have strong ion interactions. So they have weak. These have weak ion dipole interactions and strong ionic bonds with the halides. I believe that even for iodine, there's some weird like extra stuff going on where they have like interesting atomic bonding and things. Compounds containing the nitrate, acetate, perchlorate, and chlorate ions are water soluble. They typically form fairly weak ionic bonds. So the nitrate bond is not particularly strong because the nitrate ion is relatively large. So large ion means a long radius. Long radius, you are back at that point where you have a weak Coulomb interaction. Most compounds of sulfates are water soluble with some exceptions, and most compounds of sulfides are water insoluble. Sulfides have a -2. They don't like water very much. And the exceptions are sulfides with the main group, and so that means main group 1, main group 2, group 1, or the alkalis, the alkali metals, alkaline, alkalis, and then the ammonium sulfate. And it keeps going. These rules are ones that we usually will provide you. These rules are condensed into a table that will be provided you on a test or examination. So I believe you have those in your pink sheets. Most of the compounds containing hydroxides are insoluble with the exception of main group, and of compounds with hydrogen, strontium, barium, ammonium. And then most compounds containing carbonates and phosphates and sulfite, are water insoluble as well. So these are our two water insoluble ones. So we can use these rules, and I'll show you what we can do with them. And I believe that will be probably enough for today. So we'll stop around here. So let's look at sodium sulfate. The very first thing I always go to check is, does it have an alkali? And it does, so it's soluble. I don't have to read the rest. Soluble, alkali. As long as it fits one of the rules, and one of the very strong rules, then we don't have to worry about anything else. Okay, I've got a silver. I got to worry about silver. So that's a bad one. Silver's a metal. It's not, this is a metal. Metal, start to worry. To worry. And then, but it is followed by a nitrate. Nitrates are good to go. So that's always soluble. So we are good. And we can double check. We can look up here, find those nitrates. Compounds are water soluble. There is one exception, and silver acetate. Okay, so we didn't have either of those. So aluminum hydroxide. Okay, we said that hydroxides are bad news. I don't have a rule that says specifically anything about aluminum, so I'm just going to ignore the aluminum, but I do have a rule about hydroxides. The hydroxide rule was that they are water insoluble, and then I check my exceptions, none of the exceptions, so insoluble. Insoluble hydroxide. Lead chloride. Ooh, okay, well, I hear the word chlorine and I think about those halides. All of those halides, I believe, are soluble. Exceptions are compounds formed between these ions, and lead is one of these ions. Okay, so I thought for a second that it might have been soluble because of the chlorine, but that lead, we always have to worry about lead. This is insoluble. Soluble lead. Potassium and bromide, both examples of very soluble chemicals. So soluble, we've got alkali and a halide. The perfect combo. Magnesium chloride. Okay, so magnesium is an alkaline earth, so it might be a problem, but we do have a chloride there. So I'm just going to go double check my exceptions for chlorines, and I do not see mercury in there. So magnesium chloride is soluble chlorine. And then iron 3 chloride. Okay, so chlorides are usually soluble. Let's go double check the exceptions. I don't see iron as an exception, so it is also soluble. Chloride. And so that's how we would do that. Now I'm looking at the time, and I think that we are running out of time. So tomorrow we will come back and cover the precipitation reaction. Otherwise, I'm going to end the stream right now. Have yourselves a great day.